Hello, everyone. Appreciate everyone joining us today for continued customer presentations on some of the Chromalox products and processes. Today, being Earth Day, we thought it would be good to do a presentation on decarbonized thermal processes through electrification. And with us for that presentation is James Lewis. Great, this is James Lewis. He's the Business Development Manager for Sustainable Energy. He's going to has a presentation for us today. So James, with that, are you all set?
All right, thanks, Derek. Yeah, as he mentioned, my name is James Lewis, the Business Development Manager for Sustainable Energy with Chromalox. And the topic of today's discussion is decarbonized thermal processes through electrification. And we'll be able to dive into all those concepts, but first we need to get started on some of the basics to understand really what those options are. And the basics, of course, is what is electric heat. So the core technology is really pretty straightforward, comprised of four major components. The resistance wire, which passes the current and generates the heat. You have the dielectric insulation material, which isolates and protects that resistance wire. The container, the metal sheath that protects the internals, and then the cold pin and termination, which allows you to apply power to the element. So that's really what an electric heater is. It's very straightforward, but it's very versatile in how it can be integrated into larger systems. So you can see on the right-hand side there, being able to bank multiple elements together, install them into fittings, flanges, tanks, vessels, you name it. They're very versatile on how these can be adopted into larger systems. Okay, so that's obviously what an electric heating element is, but the other question we ask ourselves is, well, how do you control electric heating elements? The primary method is by the use of SCRs. And there's a number of different firing methodologies you can use, but one of the most popular would be, again, what would be called a demand-oriented transfer or dot firing method. And this works basically by shrinking down the time scale for how often that SCR is conducting and not conducting to be as accurate as possible. So you can see, just as an example on the right, a 50% load would actually shrink the timescale down to where you're on for about 17 milliseconds, off for 17 milliseconds. So that's a very, very quick and rapid firing that allows you to respond to dynamic loads and really keep up with your process very accurately. You might see the term zero cross firing that's used. All that means is really that power is turned on or off at that 0 point of the AC sine wave. There are some other firing options available, namely the phase angle. But that'll let you turn on or off anywhere along that AC sine wave. So you can imagine if you're at peak load, especially for a really, really large load, switching on that power can introduce a lot of harmonic distortion and noise on the line. So we typically only use phase angle for soft starts or current limiting, but it is, again, another type of firing option available for electric heat. And then there's also the simplified control scheme, which would be using just contactors for on-off control. That basically means you have 100% power when demand is needed and no power when it's not. And then ultimately you can combine that with an SCR to have what's called a hybrid SCR control scheme to try to balance out either a large load or to throttle the SCR side of it. Okay, so that's basically what it is and how it's controlled. So we ask ourselves, how efficient are electric heaters? And the answer is pretty simple. They're very efficient. The energy that's applied to the electric heater is entirely converted to heat at the heater, of course. Upstream, you do have what's called your I²R losses and heat dissipation through some of the power components. But those losses are really negligible to the point that you're still operating up into the higher 90 percentile for efficiencies with these systems. Also, if you couple the electric systems with renewable energy sources, you have an efficient system from generation all the way down to application. Because again, this is an electric system. Where that energy is derived is not necessarily important to the electric system. So excess energy on the grid, it could be even energy that's derived from energy storage sources or directly from the renewable energy source itself. So again, that whole loop is very efficient when you look at these systems. And we're going to talk about, the alternative technology with emissions and whatnot, but of course, because this is electric heat, there is no combustion or any of those emissions that occur, but we'll dive more into that. Okay, you can move on, Derek. So looking at what's the electric heating options on the market, they are not all created equal. Most of what you see on the market would be your low voltage systems, which are rated up to 1,000 volts. But Chromalox has actually developed the first true medium voltage element, which is known as our direct connect systems. And this operates from 1,000 up to 7,200 volts. Now, I'm not going to pick apart all the details here, but the large takeaway here is first the efficiency level of a low voltage system, about 96%. Efficiency on the medium voltage system approaching 99%. And I'll go into why that is in a few slides here. So if you look at an example system, 1 megawatt at 415 volts is pulling about 1,500 amps. An equivalent system in the medium voltage realm at 6,600 pulls only 88 amps. So that's a drastic downsizing in that type of infrastructure that's needed to support these systems. So using another benchmark, looking at even a larger system, a 3.2 megawatt system at 380 volts pulls almost 4,900 amps. In conventional circuit splits, that's about 63 circuits. Again, an equivalent system at 6,600 pulls nearly 280 amps. Conventionally speaking, you can do in about 3 circuits. So that's a reduction of about 60 circuits of not only the wires, the contactors, and fusing from a mechanical standpoint, but the time it takes to install those systems. So we start coupling all these things together into how efficient these systems are, and you can see there's certainly a lot of valid point made against some of the alternative technology. Okay, so I could talk about the numbers all day long, but it certainly helps to have a picture. So this is an example of a 2 megawatt 4160 volt direct connect system, and you can just see how that translates into the installation and really infrastructure side, where you have a very clean and simple conduit run out of the panel, just 2 circuits run through that. So you can imagine the labor it takes to install that system is very straightforward versus if we look at the next slide, on a low voltage side, now granted this is a larger system, but that concept still holds true. You can see all those wires that you need, the conduit runs, and you can imagine being out there and trying to install these systems. You have connection points on both ends there. That's a lot to work through when you get into these larger systems. And that's really where we see medium voltage take over and provide a viable solution from the electric standpoint. Okay, so if we look at basically the summary of what electric solutions have to offer between the low voltage and the medium voltage, again, because you don't need to step down that voltage, you don't need the transformer. We talked about the labor involved in the mechanical parts with the conduit and the wires. And then, of course, because you have less wires, you have fewer of those I²R losses through the wire. And that's where you see that increase from about 96% up to 99% efficiency on the operational side. And then because you're dealing with less wire, less connection points, that's drastically fewer components to manage and maintain. So drastically, when you look at the whole picture, you can see that the medium voltage systems become very efficient in terms of your commercial costs and your investment. So that's really the background on what electric heating is and where it's going to find a place in the industry. Now, again, I mentioned on that first slide that the core technology can really be vertically integrated into a number of systems. We're going to be talking a lot about the steam generator side today, just because steam generation does transcend a number of industries. But really keep it in your mind that the core concepts that we're talking about with how electric plays a part isn't just steam generation. It can go across any type of process heating or thermal process that you might have across any industry. So from a steam generation side, again, all the same standards apply with our Direct Connect series. ASME Section 1 is followed. We have the S-stamp. Traditional pressures are up to 450 PSI, but of course we can do custom designs even higher. And then the international standards that certify the heater to IEC as well as the panel up to 7.2 kV and UL up to 5 kV are all in place. And then, of course, the other components are really just what you would see out in the industry today in the low voltage systems. Between your valves and fittings, the sensors, control components, those all carry the same certifications you would expect to see. So traditionally, when we talk about where electric has a place in the industry, again, low voltage really only had a spot in the smaller systems. We saw from that picture a couple slides ago that as you start to get larger and larger, again, that infrastructure to support that just becomes very cumbersome. And that's where we traditionally saw the fossil fuel systems take over. But on the other side of that, the fossil fuel systems really weren't well designed for those smaller systems. They aren't able to trim down the loads quite as well, and they become significantly less efficient. So with medium voltage now, with our Direct Connect series, we can actually bridge that gap between the low voltage systems all the way up and directly compete and really beat out what the fossil fuel systems can offer. And we'll talk about how that all plays out in the next couple of slides. So here's just a quick look at what one of those systems might look like. I mentioned the 450 PSI. On the large end, that might equate to about 11 megawatt system with standard pressures and temperatures about 33,000 pounds per hour of steam. But again, with the electric option, it is really scalable in a linear aspect. So we talked about the SCR firing, that really only the power you need is applied. So if larger systems are needed, it's very easy to scale that into, again, the larger systems needed. Okay, so now we understand really what the electric side looks like. Now we say, okay, well, how does that compare to what is in the industry today? And of course, the conversation today is about decarbonization. So we know that traditionally the fossil fuel side is what we see in the industry. It's lasted a number of years, but we have to ask ourselves, well, what are the traditional reasons for why we're using fossil fuels? And once we understand that, we can see why electric is a viable alternative. And some of those reasons really is that the fuel source is plentiful. So if you have an abundance of the coal, oil, or gas supply, that was one driving reason why people might have used it. Again, fossil fuel boilers have been kind of at the front and center of this, so people are familiar with those centralized systems. So just purely out of that's what they know, they might be inclined to go that route. Some of these facilities might be in remote locations where there aren't necessarily strict emission regulations. The environment might not be a hazardous level, so they can get away with, with an infrastructure that doesn't need that type of permitting. Or again, the infrastructure might just support the gas system because of different fuel lines that might be in there or previous installations. So those are some of the reasons why we've seen the systems there. But if we dissect that, we can start to see where electrification can start to take over. So one of the big things that the conversation that comes up when people say, well, do I want to go fossil fuel or do I want to go electric? It's always, well, what's the cost of energy? And that is unfortunately, it's a very kind of narrow approach to looking at the evaluation, because it is true, electric cost traditionally is higher than what your gas prices are. But what we have to evaluate is that there's actually a true overarching cost of ownership that factors in every aspect of the electric versus fossil fuel. And that's where we start to see the gap shrink between the two technologies. So there's even a study there by the U.S. Department of Energy in 2019 where they did an evaluation that really just looked at the cost of energy. So benchmarking about a 3 megawatt system and looking at the cost of electric versus gas versus oil, you're able to see this huge disparity between the technologies. But again, that was a very narrow look. So if you go to the next slide, Derek, we can see to really understand the complete cost of ownership, you have to factor in all of these aspects. So number one, the thermal conversion. Again, I mentioned the efficiency of how well the system can convert the fuel into heat. Gas systems, again, they're not perfectly 100% efficient, so they have to size a larger system to factor in the efficiencies in order to support the demand that's needed. The operational efficiency, again, the evaluation the U.S. Department of Energy did was assuming that this thing was running, these systems were running at 100% the entire year. We know that's not always the case. Demand changes, there's different loads that happen, there's startups and shutdowns. So the operational efficiency side definitely plays a part when you factor in how these systems operate with those change in demand. You also have parasitic losses. Fuel-fired systems obviously have exhaust. So some of the heat that's generated goes right to the exhaust stream. So you're losing those without actually introducing that into the process. The maintenance side, you're obviously going to have a more cumbersome and complex system to control the burners and levels. And then probably most importantly is production downtime. Whether it's scheduled or unscheduled, the amount of time it takes to maintain the system and take it off and check and clean factors into lost production. So that evaluation definitely plays a part into your total cost of ownership. And then, of course, the actual cost of the equipment itself. And that doesn't have to be just the electric system or the fuel-fired system. That's all the auxiliary components that go into supporting it. So we'll dive into exactly what this looks like when you compare a fuel-fired system with an electric system to see really how this plays out. So first and foremost, for electric systems, you really have no parasitic losses, or at least negligible parasitic losses. Again, there's no combustion, there's no flue or exhaust, so you're not losing some of that energy directly to exhausting because the elements are directly submerged. So all of the energy that's created with that electric heater goes right into the water, into your process. So really the only losses are going to be from the shell or the vessel that's holding that. But with proper insulation, and even without insulation, again, those losses are pretty small compared to what a fossil fuel is going to be looking at. When you look at maintenance, electric systems are very simple to maintain and operate. In terms of a maintenance schedule, on the daily side, you have a blowdown. Again, that's not really specific to electric systems, but that is one thing to factor in. So you do need a blowdown vessel. On a monthly level, it's really just inspecting your electrical connections, making sure they're tight. But if we're talking about a medium voltage system, you're only looking at a handful of circuits, such that really the time invested in checking those connections is pretty minimal. You also want to check your water and steam leaks. Again, that's not specific to the electric systems, but it is something that gets factored in. And then on a yearly basis, it's recommended to pull the element out, inspect it, clean it as needed, make sure there's no buildup. But that can be done really on the order of hours. Some of the fuel systems we see, fuel-fired systems, it takes time to clean, it takes time to inspect. There's a lot of components working. It can take days, weeks to do this. So again, when we factor that back into production downtime, an electric system can be pulled out for a few hours and put back in so that the plant can operate continuously. Capital cost of the equipment. Again, the electric systems are very straightforward with what's needed. You have obviously the cost of the steam generator. I think you were back there, Derek. Yep. Some of the auxiliary components would be, again, the blowdown tank, the feed system. You can either have a low pressure feed system or potentially use a condensate return. And then any other additional accessories. From the electrical side, you have the power wiring and the conduit. And then, of course, your water and steam plumbing, which, of course, is not unique to the electric system. But just those components right there, that really makes up what you would need to run a standard steam generator system on the electric side. So very straightforward, and the capital costs reflect that. So now if we turn ourselves and look at what a fuel-fired system might look like, first, thermal conversion. Again, these operate under burning of fuel, and that burning fuel translates heat into the system. But those things don't convert 100%, so there is a reduction in fuel efficiency that those run at. Also, you have to factor in that these systems do run on electricity, and that's one thing that U.S. Department of Energy evaluation really didn't factor in, because those fuel systems do take energy to run with their blower systems. And those blowers can actually run a number of times before the systems are up and running. So not only do you have the electricity to run those, but you have some of the thermal operation that's wasting that heat before it gets into the process. And then as these systems operate, soot does build up. This is a combustible process, so soot will coat onto some of the components and to some other areas. And as those coat on, that does reduce the efficiency for how well these systems operate. So at the top there, I highlight that the burner efficiency you see on these fuel systems is under ideal conditions, but as they operate, that thermal conversion will actually reduce by a number of percent. Again, we look at the operational efficiency. I mentioned that the study had looked at what it looks like at 100% load all year long. We know that's not the case. We know that loads change. So the burner systems obviously typically operate in steps, and you might have 2 to 4 steps. So as these things continue to step down, their efficiencies will decrease. So really, it's ideal to keep these at 100%, but if you don't, then you will see a decrease in the capabilities of the systems. You have to factor in the startups, the turndowns, shutdowns, all that contribute to the losses, such that a lot of times with these fuel-fired systems, you actually use 2 boilers that are actually at reduced capacity. So one can operate at full while the other one's kind of throttling. So again, that factors in additional capital cost. You now have 2 boiler systems you have to maintain. And even still, you're looking at all these changes in demand such the operational efficiencies will again be decreased. And all this doesn't get factored in if we go back to that kind of narrow-sighted cost of electric versus cost of gas. It doesn't factor these types of conversations in. You also have oxygen mixture. This is a huge part of fossil fuel-fired systems. If the oxygen isn't regulated correctly, you might have poor combustion, which leads to, again, lower efficiency. It might be leading to where things aren't actually combusting at all, so you're sending fuel right through the exhaust. That can lead to different corrosive components that get created, which, of course, from pollution control and some of the emission permitting, that becomes a very big problem. So you have to make sure that you have those right controls in place for those systems to operate. Which factors right in, again, to the parasitic losses of these systems. So again, heat is just poured through the exhaust when it's not being transferred into the system. And we talked about what it looks like when you have some of these pollutants that are going through. And the important thing to remember is that those pollutants in the exhaust stream have to be treated, and they also have to be held above your dew point. If they don't, some corrosive mixtures can be created. So especially in urban environments, this becomes a very big thing to consider. But at the end of the day, this is really just factoring in how these systems, while advertise a certain efficiency, have a lot of downstream losses that get factored in. Where again, if we look back at the electric side, is a much more consolidated and a much more efficient system that doesn't have to factor in these types of aspects. So all of that really gets factored in when you start looking at maintaining the system. So I already mentioned that, again, this is a combustion process. Soot is formed, which means that someone has to get in there and clean on a regular basis. You have the burners to take care of, fans, the oxygen fuel mixtures, the treatment of the exhaust, scale buildup inside the boiler itself. All of these things have to be maintained, which means a more complex system and more to look at means higher probability for error, more likelihood that something might go wrong, and of course, eventually lead to one of those unplanned shutdowns, which now factors in a significant cost in lost production. So again, by having a more simple electric system where you don't have all of those other aspects going on, the risk for one of those unplanned shutdowns is drastically reduced. Then not only the cost of the maintenance and potential loss of production, but just the peace of mind of knowing that you have a much simpler system to operate. And also these systems require specialized skill laborers to look at this and be certified. Again, you're dealing with natural gas and combustion. You really need to have some experience in what you're working with versus, again, the electric side is a much more straightforward process. So again, don't want to harp on it too much. I know we've talked about it, but again, all that factors into if something goes wrong, that is a major hit to production, and that is a major hit to your cost. So again, I get back to that original cost evaluation of fuel-fired systems versus electric. It's really not just about the cost of energy, it's total cost of ownership. So when you factor all that in, you know, if you have one of those large pieces of centralized fuel-fired system that's producing a vital steam generation for a plant, that goes down. That's a big issue to be concerned about, and there's a lot of cost that's tied up in that might not be considered when you're just looking at fuel versus or fossil fuel versus electric. So again, I didn't want to harp on it too much, but it's important to kind of factor all of these in. And I think the next slide there shows what that. Oh no, I'm sorry. Of course, the capital cost gets factored in, and I've already kind of talked about all the aspects of it, but not just maintaining those, but the actual cost of it as well definitely needs considered. So I'm sorry, I think the next one was, I'm getting ahead of myself. So if we just pull back to summary and kind of circle back to the electric side, just to again look at that capability, medium voltage electric system, nearly 99% efficient. You don't have the flue stack losses. The footprint itself is drastically smaller because you don't have all the ancillary components. The fire tubes you can see on the picture on the right there, that large vessel to hold the fire tubes, as well as the water and steam portion of that. That smaller footprint means now you can get into places maybe you couldn't fit with the gas-fired boiler. Offshore certainly becomes more viable for the electric option. Smaller means lighter, so that's a big value from the electric side. Talked about maintenance, no moving parts, very simple to operate, just looking at connections. The SCR control means that you can respond to dynamic loads very quickly and very accurately. And then if we factor in again, it's electricity can be sourced from any number of means, even renewable energy, so that the whole picture becomes very efficient from the electric side, without the emissions, without the permitting, all of those downstream issues that might come with fossil fuel. Okay, so here's where I was kind of referring to. So back to that evaluation, when we look at electric as a way to essentially replace the fuel-fired systems. Initially, you look at the cost and you say, wow, I mean, gas wins, right? But no, you got to step back and remember, it's not just about the cost of fuel. Again, the report looked at 100% load for the entire year, but if we look at actual usage, factoring in startups, shutdowns, changes in loads, and basically how dynamic real-world applications can be, we can see that gap now becomes much smaller between cost of electric versus gas. And again, this is just the actual cost of energy. If you go, I think, to the next slide. Yep, if you kind of step back and look at everything we just talked about for the total cost of ownership with capital cost, maintenance, compliances with pollution and emission control, production downtime, installation, and you look at that over the course of 20 to 25 year ownership, we can see, okay, wow, electric does actually present a very viable alternative to what fuel-fired systems use. So I bring all this up, and I've talked a lot about it, but it really is important just to understand when we're talking about decarbonization, you're looking at what solutions you might have and what technologies are out there. Definitely a deeper dive shows that electric definitely is a more viable option in the long run than what a gas system might look like. So I know I spent a good bit of time on that, don't want to harp much more, but it was an important takeaway for the evaluation of electric. So again, I wanted to, I mentioned at the beginning, I was going to be focused on steam just to kind of talk about the technology and how it compares, because again, we're talking about decarbonization. We're really looking at how we're replacing fuel-fired systems, which again, steam generation is prevalent across a number of industries. So I thought that was a good one to focus on. But the core concepts of what electric offers doesn't just stop at steam generation. It goes into any thermal process that you might be working with, whether it's the steam generation side, whether it's superheating that steam, hot water boilers, air and nitrogen heating, water, chemical. Again, the core technology of electric is using metal sheath protection, and you can choose any number of metal grades that are chemical resistant. So it doesn't matter how nasty the process is. There's a number of metals that these electric systems can be catered to where you still get the benefits of what we just talked about from the electric side. You also have temperature management and freeze protection with heat trace systems, which still operates on the electric premise. So if we kind of dive in, I think some of the next slides, looking at now real world instances where this starts to play a part. One thing is, again, the landscape is drastically changing right now. We're seeing it day in and day out that the idea of decarbonization across the globe is becoming a bigger conversation, and we're starting to see not only federal but even statewide legislation that's actually focusing on how we can move from the fossil fuel to the electric. So this is one instance here where a state energy program has actually offered an incentive. You can see in the back there a large fuel-fired system, which is basically trying to keep up with all of these different lines, which you can imagine they're not all operating at the same time. So we talked about those operational efficiencies and keeping up with the demand. That's a huge waste to have this huge system trying to keep up with all the dynamics of these lines. So this state energy program is actually incentivizing changing out to, you can see there the Chromalox DTS system, which basically controls each of those lines. So you're only using the amount of energy you need for those lines, not relying on some oversized or unused or idling fuel-fired system. So I encourage everyone, again, this is statewide, so some of the changes, some of the programs might change from state to state. So investigate in your state. I'm sure there's some incentive programs, and if there aren't already, certainly as we move on and this conversation continues to grow, there will be more incentives that come about. So now to try to take it away, I know, again, we've been harping on the steam side, just to think about some other industries that are out there. This is one from the oil and gas industry where we see, again, these large gas-fired systems are brought in where they're not even really sized for the application. They're really just defaulted to a standard burner size, and as they need to operate, they operate. So there's drastic losses in these systems versus if you look at an electric alternative, for example, a knockout drum, using what's called in the industry a heater treater, you might only need a few kilowatt out of the electric system. So being able to localize that demand with a small scale electric heating element means that you're only using what you need to accomplish that goal. You don't have to rely on these large systems that basically work intermittently or that idle for long periods of time. If you move downstream, again, a cold flare knockout drum, same premise. You don't need that large system to support that. And we offer at Chromalox a number of product solutions for these types of applications. Some of these tanks can get pretty big. So we do have solutions like our LTFX, which basically means that you don't need to drain the tank. You can install the heater, which has external wells, and the heating elements can be removed, all while the internal tank is maintained. Also, our heat trace is able to wrap around these and try to keep a nice idling temperature, freeze protection. Again, all that from an electric standpoint is a way to take away reliance on those kind of just general fuel-fired systems that are used to operate. Another existing system here, this picture I think is great. It's worth 1,000 words, right? So these are some three-phase separation heaters at an oil and gas facility. These things just sit there and idle, and again, they're not sized for what they need. So you can just imagine how inefficient these systems are when they run. Where if you look at what it might be from an electric side, again, you're able to cater to the exact needs of that process as it's needed. Again, you don't need to idle these or run intermittently. You just need to operate what it takes to fulfill that separation process. Moving into another industry, another concept is district heating. And I bring up this one because this is a great concept where you kind of get away from maybe the rural environment and you're talking about something that's down in an urban area. Again, traditionally you'd see a large centralized fuel-fired system that would be providing steam or hot water to the district of commercial buildings. You can imagine that there's a lot of dynamic load changes that are happening with all the different facilities. But more importantly, we talk about, again, the pollution control and some of these toxic gases that come out. Nobody wants that down in an urban environment. So now that we have our direct connect technology where we're able to scale up to larger systems and still be an efficient infrastructure, district heating is a huge thing to look at that provides very significant savings and a much more efficient system compared to what you would see with the fuel-fired. Okay, and just to hit a last few case studies home of what we've talked about today. Here's one example at a Middle Eastern sulfur plant. The reason I bring this one up is, again, talking about hazardous environments, whether or not it's something because of hazardous gases in the area, or maybe the environment's just extreme. Again, you're out in the desert, you have very hot days, very cold nights, you have the sand. Using a fuel-fired system, again, that's a lot to contend with. Electric systems, we have the certifications to support it, we have the designs to support it, and we provide these systems to some very extreme environments and still see success in them. So I thought this was a good case study for showing it doesn't have to be an indoor safe environment, it could really be an extreme or hazardous environment. This case study is a great one of an alternative to centralized systems. We see a lot in hospitals and research facilities where reliance might be on a fossil fuel system that is centralized. But again, you can imagine it's supporting so many different processes. All the change in loads really puts a strain on the boiler systems. Whereas electric, again, very scalable, even down to small systems, that having a point of view steam system might be more valuable or viable than a centralized system. So I thought this was a good case study just to show how versatile the electric systems can be, where it doesn't always have to be centralized. You can do point of use and get a lot of value out of it. And I think this is my last case study. So again, I've talked about this one a lot, but just to kind of round it with a real world example of an ethylene production facility. We talked about the SCR control and how easily electric can be scaled from a 0 to 100% duty cycle versus the fossil fuel system. So if you're not operating continuously, if you have intermittent or changing demand, again, these systems can keep up in a 1-to-1 ratio of what you need. So if you only need 50%, you get 50%. You're not idling, you're not turning on large banks or stages of the gas systems. You're able to introduce exactly the type of system you need. And I think this is my final slide. So again, what we covered today, just to bring it all back together, is really just looking at what electric heating is, especially with Chromalox's direct connect medium voltage technology. We can see that now we have bridged the gap. It's not just these small scale systems compared to fossil fuel. It's now everything in between with the direct connect. So with the changing landscape and the emission control and trying to be more efficient, seeing a greater growth of renewable energy sources, all of this gets factored in to see whether it's steam generation or process heating. Any of those thermal processes can rely on electric to replace those fuel systems. So again, we want to see, as the industry is changing, decarbonization is becoming much bigger of a conversation globally. I hope this was valuable to see exactly how this all boils down into a real world cost of ownership of the electric system versus those fossil fuel systems, and again, how electric can be a viable solution. So with that, I believe that was all I had for you.
We appreciate everyone joining us today. We'll stick around a little bit in case some other questions do come in. James, nice job. Appreciate you going through that with us, and a lot of opportunities to come, I'm sure.
Thank you, Derek. Recap everything I just said was appreciate everyone taking the time to come join. So if there's no more questions today, but something comes to you after the fact, feel free to reach out to me. You can see my email there on the slide, or connect with me on LinkedIn. Happy to answer any questions, because I know I did run through this pretty quickly. I was trying to be respectful of everyone's time and stay within the time frame we had. So if something comes to you after the fact, by all means reach out and I'd be happy to discuss further.
Excellent. Thank you, James. And thank you all for joining us, and appreciate your time.
Yeah, thank you.